Here in section 2.3, we learned that many common problems that come up in physics or engineering or just modeling all sorts of different situations with mathematics involve differential equations. This is why differential equations is really one of the most useful fields in all of mathematics. So this is all in section 2.3 in the book. This section really just presents a bunch of different examples, so that's what I'm going to do here. I'm going to just give you an example here of solving a problem where you have liquid pouring into and flowing out of a tank. I'll read the problem for you. A tank with a capacity of 500 gallons originally contains 200 gallons of water with 100 pounds of salt in solution. Water containing 1 pound of salt per gallon is entering at a rate of 3 gallons per minute, and the mixture is allowed to flow out of the tank at a rate of 2 gallons per minute. Find the amount of salt in the tank at any time prior to the instant when the solution begins to overflow. Find the concentration in pounds per gallon of salt in the tank when it is on the point of overflowing. Compare this concentration with the theoretical limiting concentration if the tank had infinite capacity. So there are going to be several things we'll have to do in this problem, but first and foremost, we'll have to set up notation. When you have a problem like this, you are the one who has the obligation to set up the notation, and that includes very clearly stating what the units for your functions and your variables are. How are we going to do that? Well, we want to talk about the amount of salt in the tank. So I'm going to start by saying let Q of t be the amount of salt in the tank at time t. Now, before we even finish this, we have to be clear about units. What are the units going to be? Well, the salt will be in pounds, so I'll say the amount in pounds of salt in the tank at time t. What's a natural unit for time in this problem? We're going to say time will be in minutes. So now we have a variable t and our function q of t, and we want to ask what information is given in this problem and what is it asking about? Well, it's asking things about the concentration of salt at time t, and concentration is just the quantity here, how many pounds of salt, divided by the volume. So you get pounds per gallon for concentration. If we can understand Q of t, the amount of salt, if we can get a formula for that for any time t, we'll be able to get a concentration just by dividing Q of t by the volume at time t. Let's tackle the easiest part of this first. The volume at time t is not constant. The tank starts with 200 gallons of water, but since each minute 3 gallons of solution comes in and 2 gallons go out, we can write that the volume at time t, it starts at 200 and increases by 1 gallon each minute. So we can just write right away is 200 plus t. And again, this is in gallons. I'm not going to put in gallons because we already know t is in gallons. So for this to make sense, this will have to be in gallons. I'll just write here, gallons. Okay, now how are we going to get to the concentration Q of t? Well, here I've repeated that how we define Q of t. We were told an initial condition, and let me go back to the problem. The initial condition says it originally contains 100 pounds of salt in solution. In terms of our function q, that will be the initial condition that Q of 0 is 100. And now I'm going to stop writing down units because we know this will have to be in pounds and the time t will have to be in minutes. We want to set up a differential equation that the function q must solve. dq dt, that's the rate of change of q, must be the rate that salt comes in minus the rate that the salt goes out. And it's important to keep the unit straight. Q is in units of pounds, T is in units of minutes. So these rates, dQ dt, whenever you have a derivative, the units are the quotient of the units for the function divided by the units for the variable with respect to which you're differentiating. In other words, the rate in and the rate out both should be in pounds per minute. Now, what is the rate in? Well, we're told that 3 gallons of water come in per minute, so we have 3 gallons per minute, and the concentration of the water coming in is 1 pound per gallon. So that ends up being 3 pounds per minute. That's the rate that salt comes in. How fast does salt go out? What's the rate at which the salt is leaving the tank? Well, 2 gallons per minute of solution is leaving. And we'll assume that within the tank there's perfect mixing so that the solution is all at some uniform concentration. But what is that concentration of salt in that solution? Well, that concentration is the amount of salt, Q of T, divided by the volume at time t. Remember, we said right away the volume at time t was 200 plus t. So the rate the salt is coming in is 3 pounds per minute. The rate going out is 2 times Q of T over 200 plus T. Check the minutes here. This is gallons per minute. Q of T is in pounds, and this 200 plus T is in gallons. So we have gallons per minute times pounds per gallon. Again, this ends up being in units of pounds per minute. So now we set up our differential equation. That becomes dQ dt equals 3 minus 2 times Q of T over 200 plus T. And we know Q must satisfy this differential equation with this initial condition. So when I combine the two, we have an initial value problem, and we must solve this initial value problem. And this differential equation is a simple first-order linear differential equation. The coefficients are continuous everywhere. It's going to have a unique solution with this initial condition. So here's the differential equation that we set up. In order to solve it as a first-order differential equation, we're going to use an integrating factor. So we're going to write the differential equation in the standard form for the use of an integrating factor. What will that integrating factor be? The integrating factor will be e to the integral of p of t. That's the integral of the coefficient on q here. That's the integral of 2 over 200 plus t dt. That's the integral of let me erase that. That's e to the integral of 2 over 200 plus t is 2 times the natural log of 200 plus t. We don't need absolute values here because t is going to be greater than or equal to 0. The whole situation begins when t equals 0, and we're only interested in positive t's. And how does this simplify? E to the log 200 plus t is just 200 plus t. And because of that 2 there, that will be squared. So there's our integrating factor, which I'm show you again here. We multiply through by the integrating factor, and the differential equation becomes this. Remember, when using the integrating factor, the integral of this left side becomes this. The integral of the right side very easily is seen to be 200 plus t cubed, plus we have our arbitrary constant c. All solutions to the differential equation look like this, or dividing by the 200 plus t quantity squared. Q equals 200 plus t plus a constant over 200 plus t. Before we go any further, check this result. Everybody should get used to checking results whenever you claim to be solving a differential equation. I'll leave that to you here, but how would you check the result? You just have to compute dq dt, and add that to 2 over 200 plus t times q for this function q, and check that what you get is 3. You can pause the video while you check the result. Our initial condition, in order to solve for c, we use our initial condition, q of 0 is 100. So what is q of 0? Q of 0 here, plugging in t equals 0, is 200 plus c over 200 squared, and this must equal 100 by the initial condition. When we write the equation that this has to equal this, we get 100 plus c over 200 squared must equal 0. In other words, c over 200 squared is minus 100. C is 200 squared is 40,000. I'm sorry, 200 squared is 40,000. C must be negative 40,000 times 100, which is 4 million. So here we have our actual function q of t, which tells us how much salt there is at any time t. It's 200 plus t minus 4 million over 200 plus t quantity squared. This will be valid for all times t greater than or equal to 0. Now, in order to really answer the question correctly, we should go back, read the question again, and make sure we're answering each question that's asked. The question says, find this amount of salt in the tank here at any time prior to the instant when the solution begins to overflow. There's a little problem here in the printing of this slide. Well, the function we had for q of t is 200 plus t minus 4 million over 200 plus t squared, really isn't valid for all times t greater than or equal to 0. It will stop being valid as soon as the tank starts to overflow. And that means we'll want t less than or equal to 300. Why 300? Because it's a 500-gallon tank, starts with 200 gallons of water, so after 300 minutes, it's reached a capacity of 500, and after that, it starts to overflow. So the tank begins to overflow when t is 300. And we just find that q of 300 is 500, that's the 200 plus 300, minus 4 million over 500 squared, which is, when you get out your calculator or do some computations in your head, 484. So what is the concentration at that time? The concentration is just the amount of salt at time 300 divided by the volume. So this 300 is in, I'm sorry, that should be a 500, which is what we have here. The amount of salt at time 300 divided by 500, which is the volume of the tank, so that's 484 over 500, which is 0.968, just using a calculator again. So the concentration is close to 1. It then asks us to find the concentration, to compare this concentration with the theoretical limiting concentration if the tank had infinite capacity. Well, if the tank had infinite capacity, and we would find, and then it would be true that q of t would be 200 plus t minus 4 million over 200 plus t squared. Now for all t greater than or equal to 0, what would be the limit as t approaches infinity of the concentration, which would be q of t divided by 200 plus t. Remember, 200 plus t is the volume of the tank at time t. Well, that would just be the limit as t goes to infinity. Q of t over 200 plus t is easily seen to be 1. That's 200 plus t over 200 plus t minus 4 million over 200 plus t quantity cubed. And it's easy to see that this second term goes to 0, so this limiting concentration is 1. And remember, the units here will be in pounds per gallon. So if this just kept going on in a bigger tank, it eventually would approach 1 pound per gallon. And that's not surprising, because the water that's being pumped into the tank contains 1 pound of salt per gallon. So in the limiting situation, the initial concentration, which was actually only 1/2 pound per gallon, becomes less and less important, and the concentration becomes dominated by the concentration of the incoming water. And you'll see that when the tank is overflowing, that concentration is 0.968, which is already pretty close to the limiting value.